Hello everybody, and welcome to my talk about the development of inline closed-loop control and progressive die stamping using finite element simulation for the virtual IDDHG 2020. My name is Florian Steinlehner and I'm a research assistant at the Chair of Metal Forming and Casting from the Department of Mechanical Engineering from the Technical University of Munich. I will present results from an ongoing work in the field of progressive die stamping and how to influence and control strip vibrations. The work was done in collaboration with the company Man at Work, Germany, the company Forming Technologies, and the University of Waterloo, both Canada. I will hold my talk in a typical structure, beginning with the introduction and motivation, where I'd like to mention the most important characteristics about progressive die stamping and why it is important to avoid and control strip vibrations while operation. I will also explain briefly what factors are influencing the tendency for strip vibrations. In the next point, I'd like to take a closer look on the lifting process of the strip, which is happening while the material is progressing through the die. I will also explain the challenges for the controlled strategy resulting from the lifting process. In the third chapter, I will show the details of the implemented co-simulations between Abacus and MATLAB Simulink and the characteristics of the finite element model and the used control strategy. The results of this control strategy are shown for 4 different strip layouts in chapter number 4. After the results, I will end my talk with a summary and a conclusion of the presented work. Our motivation for this work is based on the progressive die stamping process and a more robust operation for increased outcome and improved part quality. Progressive die stamping and progressive die forming are typically used for a high volume production with a fast running process. The produced components are made from many different industries, like for example the automotive industry or the electrical industry, and are used in a variety of applications. While the desired part is produced with the help of multiple manufacturing processes like punching, bending, and cutting, it is connected to strip material via stretch wrap connectors, helping to keep the part in its desired position and to progressively transporting it through the die. A selection of parts for different applications with diverse types of stretch wrap connectors and different strip layouts are shown here on the right. The reachable maximum stroke rate of the progressive die stamping process is usually determined by the slowest single operation in the process. This slowest operation is often a forming process which requires a slow forming speed, like embossing or coining. But there are also processes where the maximum stroke rate is limited by the occurring strip vibrations along or across the strip's progressive direction. Strip vibrations can destabilize the progressive die process and can reduce the possible outcome and the part quality. This can have various reasons with different levels of consequences. If the vibrations on the strip lead to a collision between the strip and the tool or causes the strip to jump out of the guiding gap of the strip lifter, the consequences can lead to a crash of the tooling, resulting in a significant damage of the surrounding components. Strip vibrations can lead to a reduced part quality when the positioning of the strip and therefore the positioning of the part is not maintained over the duration of the process. This can happen if the positioning pins miss the pilot holes for accurate positioning before the strip gets clamped, or the blank gets clamped by the binder in an inaccurate position. This leads us to the question how the occurring vibrations on the strip can be reduced while maintaining a high stroke rate and a satisfied production quality. To answer this question and to reduce the strip vibrations on the strip, with an active control strategy, we first need to know which influences are affecting those vibrations and in which manner. There are, of course, many passive influence factors, like the strip layout, the geometry, of the stretch web connector and the overall part design, which is usually given and cannot be changed. There are limitations in changing the passive factors, and usually one cannot change any of them after the progressive die tool is manufactured. Once the tool is in operation and there are strip vibrations remaining after each stroke, a reduction of the stroke rate is often the only solution without the need of a costly reworking of the tool. In this work, we try to implement more active influencing factors in a new designed progressive die tooling. By the use of a servo-driven feeding machine, or by replacing the passive spring-loaded strip lifters by linear actuators, the trajectory of the strip while being lifted or while being fed can be actively adjusted. In this work, we are focusing on controlling the strip lifter's position to reduce the strip vibrations on several reference points on the strip with the help of a simplified finite element model of a progressive die tool. I will now continue to take a closer look at the lifting process that will be controlled with the help of the shown approach. To understand the operating principle of the lifting process, I will use this model of a three-stage progressive die tool to briefly explain the important issues. Shown here is a feeder system and a tool. The tool is consisting of a piercing station, a forming station, and a cropping station at the end of the process. Each of these stations has multiple strip lifters on each side of the strip. I will now explain the typical trajectories of the tooling's top plate, the binder, and the strip lifter by moving through the important phases of one stroke of progressive die stamping. Therefore, I will use the side view of a progressive die tool and a cut view through the cross-section of two strip lifters where the part is simplified, represented with a Morse point. Beginning at the top dead center of the stroke, the top plate is at its upper position and the binder is connected to its wire springs. The spring-loaded strip lifter held the strip in its upper position at feeding level. The press ram is then pushing the top plate and the binder simultaneously in a sinusoidal curve into downwards direction until the binder has contact with the strip and the strip lifter. The strip lifter is then pushed downwards while the middle part of the strip is following with a delay, and its spring is compressed until it reaches the level of the die and the strip becomes clamped between the binder and the die. After the strip is clamped in its designated position, the forming and piercing punches comes into action. Every possible impact or vibration resulting from those forming operations will not affect the strip and is stamped and gone until the binder releases the strip. After the strip is released, the strip lifters are pushing the strip following the binder and the top plates towards its upper position until the lifters reaches their initial position. The upper position of the strip lifters is characterized by a hard stop, which leads to an immediate stop and results in a hard impact into the strip, which leads to strip vibrations. This vibrations causes a clattering of the strip in the guiding gap of the lifters, as we can see here in the left bottom corner. The moment of impact due to the hard stop is the point to control and is basically dependent on two things. One is the trajectory of the strip lifter, which can be controlled by a closed-loop feedback control approach. The other one is an active compensation of the inertia effects resulting from the lever arm and the clattering of the strip in the guiding gap, which can be controlled by a feed-forward control approach or a model-based approach. Considering this information about the progressive die stamping and the lifting process, I will now continue to give a brief overview about the structure of the co-simulation and the design of the finite element model and the control strategy. The co-simulation is structured into two big parts, represented by a finite element block, and a controlling block. The co-simulation is done using Abaqus Explicit, Abaqus Python API, and MATLAB Simulink, and uses mainly the Abaqus restart option as an interface between the two main blocks. The first step is to create the assembly of the finite element model and to define the desired initial configuration and boundary conditions in the complete Abaqus environment. The initial input sheet is then saved as a text file and sent to the Abaqus Explicit solver by MATLAB using Abaqus command controls. The simulation stops at defined restart points, and the needed results data is obtained from the Abaqus result file with the help of the Abaqus Programming Interface API. The load and displacement curves of the striplifter and the reference points on the strip are then saved to be later accessed by MATLAB and Simulink. Simulink uses a closed-loop control strategy with a PID controller and a given reference trajectory to calculate a load curve for each single strip lifter based on the displacement of the reference point of the strip. MATLAB then writes the calculated load curves for the following restart increment into an input sheet and starts the simulation by calling Abaqus command controls. Those iterations are repeated until the end of the simulation time is reached. Let's now have a closer look at the finite element model. The shown assembly of the finite element model is a simplified representation of a progressive die tooling with 3 stages. Module A is representing a blanking stage with rather wide dimensions, which usually shapes the design of the strip layout and stretch wrap connectors. Module B is representing a rather narrow, deep drawing station, and Module C would usually be a cropping station at the end of the process. Every module has one strip lift on each side of the strip. There are 2 general models used for this work. One is the reference model, where the strip lifters are spring-loaded and are getting pushed down by the downwards movement of the press ram and of the binder. The other model is the controlled model, where the strip lifters are moved by a load-controlled single force acting on them. In both models, the tool consists of rigid shell elements, R3, D4, and the strip is made out of deformable shell elements with the type S4R. The writing frequency for both the field and the history output and the frequency of the restart is chosen to be a multiple of 360 Hz to fit to the frequency of the controlling block of the co-simulation and to the crank angle of the progressive die tooling. We investigated 4 different strip layouts with the just shown model. Every strip had a thickness of 0.5 millimeters, a width of 100 millimeter, and a length of 500 millimeter. The strip layouts were meshed with quadratic elements and a minimal element size of 1 millimeter, resulting in an average stable time increment of 4.5 times 10 to the power of -7 seconds. All of the simulations are calculated with an explicit solver without using mass scaling. The first strip layout is a full strip without any parts on it. This layout was chosen due to a fast simulation time and to tune the PID controller in the controlling block of the co-simulation. Also has this strip layout very little vibrations because of its overall high stiffness. The second strip layout is a double-tracked layout with 3 carrier strips, 2 on the outer side and 1 in the middle of the strip. This configuration is often used for small parts and highly affected to strip vibrations along and across the progressive direction of the strip. The third strip layout is a single-tracked configuration with 2 outer carrier strips. This layout has a medium stiffness remaining along the strip. The last configuration is also single-tracked, but has on one side a carrier strip and is therefore often used for small components due to the single carrier configurations. This strip has little stiffness across the strip's progressive direction. The control block in MATLAB Simulink uses the displacement curves of the reference points on the strip to calculate a load for each single strip lifter. This is done using a reference trajectory, which can have multiple different forms, like a linear function, a sinusoidal function, or a higher degree polynomial. For this work, a step response was used to focus on the transfer function of the total system. The desired reference trajectory is then compared with the current position of the reference point, and the error is calculated. This error is calculated from the PID controller into a load, which is transferred into the abacus model. A classical PID controller consists of three main terms. The proportional term puts a gain according to the current error. The integrational term is taking the past behavior of the error into account, while the derivative term acts against fast changes in the error signal. One PID control loop is implemented for each single strip lifter, which makes 6 parallel control loops overall. I will now present the results for the numerical testing of the co-simulation approach. First, a tuning of the PID controller was done using the Nichols-Zegler approach on the full strip configuration. Therefore, we set every parameter except the Kp to 0 and increased the Kp parameter until we had uniform vibrations on the strip. This gave us the critical parameter Kp critical and the T critical. Those critical parameters allow us to calculate every parameter for the P, the D, and the I term of the controller. To obtain even better results, we made slightly modifications by manually tuning the parameters in small ranges. This was possibly necessary because of the nonlinearity of the FEM model. On the right side, you can see the reference vibrations obtained with the spring-loaded model and several attempts while tuning the PID controller. If we choose the parameter too small, we will end up being too slow in the lifting process. If we choose the controlling parameters too high, we will end up risking a collision of the part. On the right bottom center, you see the optimized controlling parameters. Here I will show you the results for the full strip and the double-tracked, triple-carried strip layout. For both cases, a good reduction of the remaining vibrations on the strip after the lifting phase was achieved. The vibrations on the double-tracked strip layout were reduced about 50%, even though the controller was tuned with the full strip configuration. In addition to the achieved results of the vibration control, the different parts of the strip are vibrating in a more in-phase and a more homogeneous way on the right side from the double-tracked strip layout. Similar results were achieved for the two single-tracked strip layouts. Both of them are highly affected by strip vibrations for the reference uncontrolled configuration. The double-carried layout showed the smallest influence of the controlled strategy and seems to not be as controllable with the chosen PID values as the other strip configurations. Therefore, the single-carried layout can be controlled to a vibration decrease of more than 50%. The fact that the remaining vibrations on the strip are getting to vibrate in phase is an additional benefit of the controlling strategy. For further work, the different strip layouts should be investigated and should be tuned individually. The strip's stiffness along and across the strips seem to have the biggest influence for the tuning process. This leads me to the end, where I have a brief summary and a conclusion. A co-simulation interface between Abacus and MATLAB Simulink was implemented using the Abacus restart option in this work. Closed-loop feedback control maintains the desired position of the rigid body movement of the strip lifter. A feed-forward or a model-based control strategy should be implemented to consider also the dynamics of the system and the flexible behavior of the stretch web. More effort will be put into trajectory generation to reduce the initial impact causing those vibrations. The model will be extended to forming and to feeding operations to enlarge the control strategy. Thank you very much.